This is PyEmu, a multi-purpose scriptable x86 emulator. I'm Cody Pierce, as you can probably read. What we're going to do is we're going to go over a little bit about emulation. We're going to go over a little bit about Python and reverse engineering using emulation, and then we're going to go into the actual tool and the methods I provide and how it works and whatnot, and then some case studies. So how many in here use Python? Good. I was thinking maybe the room would be half Python and half, Ruby people or something. So, good. So let's go ahead and get started. This is my idea for the whole thing, a Python emulator. And just a little definition about emulation. It's a very broad term, but in essence, emulation is a software or hardware that replicates a processor and allows a system to run that software that was perhaps compiled for, a different architecture. I say it's a broad term because I'll talk about two different distinct ways that common emulators work. And, it gets used in that sense, here and there, different places. They, can mean various things. So I'll try and define that a little bit. Just a quick history. IBM were the first people to actually use emulation, at least in any sort of modern sense of the word. What they did is they created an emulator for the 770 processor, and they provided it for their System 360 platform. So what they told their customers was, hey, you can take your existing compiled software, your code you wrote and whatnot, and just take that over to the new System 360, and it'll be emulated as if you were running the old platform. I think it was a System 700 or whatnot that was the old platform. Now, that allowed customers to easily switch to the new architecture and adopt all the new, system that they were trying to provide. And that's a good sense of how I'm using emulation. Running a binary, emulating a binary that was compiled for a different platform, or executing code without the process, or in my sense, I'll execute code without the process actually running. So the two categories that I mentioned earlier, system emulation is the first one. System emulation is what is the most popular right now, and I include virtualization and hypervisor in that category. What that does is provides a complete implementation of an architecture. We'll go over just a couple of the different things that it provides and how it works, but in system emulation, you would be able to run a guest operating system. Parallels people running those in Mac and VMware running different sorts of operating systems. For PyEmu, I focused on more instruction emulation. And its concern is simply emulating the processor or instructions that the CPU would execute, as it runs. So we'll try and kind of show how those are a little bit different and whatnot. For system emulation, like I said previously, you'll run a full OS. It handles access to various external devices, allows simulating a full system. And that includes, as we'll see right now, the BIOS. They have to initialize storage, memory, CPU, execute a bootloader. Anything you would expect a normal system to do. You have interrupts, the exchange between the processor and the external hardware will be done with system emulation. And of course, I/O, it's pretty straightforward. You'll have a mouse, keyboard that are all emulated and in different modes. It'll just access the real hardware or whatever it wants to do. And as far as system emulation goes, like I said, it's used the most right now for doing virtual machines and whatnot. And actually the big processor companies are providing a layer for virtualization inside of their architectures. And the reason they do this, and it's pretty recent, I think Intel did their paper on IVT last year and started, trying to get developers to look at it and whatnot. But what they decided is that it's a big market. VMware, since 1998, has grown substantially in the market. I use it every day. Most people in the field use it every day. It's just a great product. They decided that they were going to cater to that and provide extensions to lower the overhead on virtualization and hypervisor and things like that, and give people the ability to, interact more and closer with the real processor to do their virtualization. AMD's is called AMD-V. Intel's is called IVT. And Intel also has one for their Itanium processor that can do the same thing. Although, I don't know who uses Itanium much. anymore. So as we carry on, examples of these, a couple open source, Box, QEMU, and then a couple of the big three, VMware, Virtual PC, and Parallels, as all of y'all. How many of y'all use VMware and things like that? Yeah, see? They've grown so much. It's so useful now. But next we'll go into instruction emulation. Instruction emulation, as opposed to system emulation, is more of a utility emulation. Focuses on strictly executable or binary and CPU emulation. Emulate the logic of the instruction sets. We don't have hardware support. We're not going to allow you to run, a Quake or whatnot in PyEmu. You won't be able to script out, the next World of Warcraft cheat in PyEmu. You can't run a guest, and a couple of those examples are IDA x86 and PyEmu. I don't know of many other that fall in this category right now, but as we'll see, I think that it's going to be a useful thing, like in reverse engineering that we'll go into in a second. So, as I say that, emulation and reverse engineering. I've made this a large piece of this talk because I think that, at least with a utility like PyEmu, you have to have something to solve. You have to have some reason to use it, and that would be in reverse engineering, at least. I'm sure there's many other uses, but reverse engineering, vulnerability research, exploitation development, those sort of things fall into a perfect category where this can be used. Must be capable of static analysis, especially malware people don't have the ability to actually execute a lot of code, even with VMware. I've ran enough viruses and malware in VMware, I'm still scared. I don't know, exactly what's going on and things of that nature. So it must be able to do static analysis. And I have malware analysis. I already went over that a second, but is another good use for this. So the first, and I have three different kind of examples or uses that I feel are pretty obvious. And I'll go into why and how emulation may be able to solve something like this. So complex code paths. Complex code paths are abundant in any sort of large program. I have an example next of Microsoft Excel, but it's a fairly large binary. And various thousands of functions, hundreds of branches in a function. So when you look at a function, you may have a couple thousand functions, but what you don't realize is that each of those have, hundreds of basic blocks and all these different instructions that are going to get executed. So understanding this code path is critical when you're doing, for instance, when I've looked at file format parsing. These functions that do file format parsing are incredibly complex, and understanding exactly what's going on is pretty critical to, deciding where a vulnerability is, where something might lie, things of that nature. So with emulation, what we can do is quickly simulate these paths. I want to go here to here, I want to go through these basic blocks, or even here's a dark piece of code that I can't get to execute. I want to execute it and see exactly what it's doing, even though I can't get the process in real time to jump to those instructions. And as I said, this is actually from an example we have in our office taped on the wall that is actually 3 pages. If you notice, I cut this off. It's 3 pages long. And if you look at it, I don't know how many people use IDA in here. I think that's the largest room so far I've seen that question asked. And people do. So the green instructions and the red, or the green lines and red lines are different branches or different ways you can go on a branch. These are all basic blocks. If you look at this, you would probably just, go get coffee and forget about it. It would take you forever to reverse this out. And even with live debugging or whatnot, you would have to single step through a lot of these and check all the memory and things of that nature, and it's kind of difficult to get through and navigate. So the next one is ambiguous code. And it's kind of hard. What I try and call ambiguous code is various unknown basic blocks or blocks of code. And inside those blocks of code, they have multi-level calls. You'll have multiple calls in a single basic block with only one single branch at the bottom, right? So you also have lots of global variables used, lots of local variables used, lots of pointer derefs, all sorts of things in a single block of code. And if you look at it and just look at that basic block, it's impossible to kind of tell what's going on because there's so much information that is needed that you have to figure out a way to define all those things. Figure out a way to say, okay, this is accessing this piece of memory, and this variable is used for this, and it contains these different things. So we can do this with emulation. We can set up different pieces of data, emulate, and determine results. And this is the example I have. You get different global variables, stack variables. I don't have any arguments in here. You see a structure being dereferenced at some point. And what is that, 4, 5 calls? So if I looked at this basic block, I would say I really don't know. And it's important to know what each basic block does. The second one is code obfuscation, which is gaining ground a lot in modern binaries and modern compiled software because people want to protect their intellectual property. Reverse engineering is becoming a lot more apparent to the rest of the industry. It's becoming well known, and a lot of companies are employing reverse engineers to do these sort of things. So with code obfuscation, people want to try and protect that a little bit from the majority of reverse engineers or other different companies trying to steal intellectual property. And a big piece of that is hindering static reverse engineering. It can be used to confuse IDA. I've seen some disassemblies that just look completely wrong, instructions that are impossible to use right there. But emulation can aid in breaking that down by actually executing what is in those blocks of code and trying to gather what information is being exchanged or how relevant that information is. And I have a simple example here. And as you can see, it could be done by hand, but with automation we could do it a lot easier. And then time. I said I had 3, but I actually have 4. And time is the single most valuable resource related to reverse engineering. Someone laughed at the next bullet, impossible to quantify. Yes, I'm saying that time is impossible to quantify, but it's because many factors go into saying how much time will it take to reverse engineer these pieces of a binary. And those factors include size, complexity, and proficiency, which vary enormously in modern binaries. So I have an example here, again, Excel, and if you look at the bottom, this is a list of all the functions that at least IDA can recognize, and it's 27,754 functions, which may not seem a lot, but if you start looking at the length of the functions, and it's in hex if you can't see it, these functions, at least, I think it was 900 or 1,000 of those functions, maybe more, are over 4K of instructions, and that's going to be impossible to reverse engineer. But if it did take you 10 minutes per function, and you had 27,000 functions, I calculated this out. Oh, yeah, let me step back. 10 minutes per function. I don't know anybody that can reverse engineer that fast, especially things that are 4K or have more than, 1,000 instructions. So if we had Superman doing reverse engineering and it took 10 minutes per function, that would still take you 193 days, which, I guess I did quantify time a little bit. So with this massive amount of information in reverse engineering, and y'all know that the most critical piece of reverse engineering is organization. Being able to get through binaries, being able to understand functions is probably the most important thing. You can learn the instruction set pretty easy, but it's the efficient people that get through binaries.